Hello, I am back with the next portion of this tutorial, and this portion is going to be covering specular lighting, and we're going to start talking about the Phong and blend lighting model first. Then we're going to go into the cook toward specular um, models. Then we're going to start talking about speeding considerations for unity theory and dual specularity. However, I do need to start out with a little bit of theory to just explain what specular reflections are in the first place. Okay, so I have this little diagram that I created in Paint to try and explain um, how specular reflections work and also how diffuse reflections work. Um, so let's say that we have an object, a 3D object, and it's smooth, and we have a light source shining on it, and it's not a laser. If it was laser, I would have drawn it as one single line, but this is more of a flashlight, and so a portion of the surface is being illuminated by this flashlight. And because this surface is completely smooth, um, it's going to have a normal which faces, it's going to be perpendicular from the surface. The normal also is equal distant between, um, the angle is exactly half of the angle that you would have from the incoming light, um, incoming light source's angle to its reflected light source's angle. Also, the incoming light source's angle is the same as the reflected light source's angle. And so, if the light comes in from one angle, and it must be reflected at that exact same angle, but 90 degrees away from, well, it's mirrored on the, it's mirrored over the 90-degree angle um, point, which is a vertical line. So your viewing angle is your eye, basically. It's an eye or a camera or just something that is looking at the object, the model, that light is shining on it. Let's draw that as a flashlight. Actually, it's kind of hard to draw a flashlight. A flashlight would need to be up there anyway, but you can kind of see what's going on. As the viewing angle rotates, like let's say it's down here, you don't see the reflected light. As it starts to get closer to the angle of the reflected light, the more likely you're going to see the specular. So right now it's here, but if we were to you were to bring your, let's say your face or your head into a lower angle, and you're starting to get closer to 90 degrees, like let's say you've now moved your head so that you're within this area of reflected light, you would be able to actually see the reflection of the light, and that creates a shiny surface. So what you would see now would be something like let's start to see something sort of like this. So you would see this intense highlight as your eye got closer to the reflected angle. So the light is coming in here, being reflected in this direction, and your eye is looking right here, so you can see the light reflection. But previously your eye was looking over here where you don't see the reflection. So that was the old viewing direction, but then we moved it to over here. So that's basically what's happening in this diagram, and this is for smooth surfaces and specular highlights. So a rough surface is, if the surface is really, really rough, you have your, it's modeled by Lambertian function. But let's say that the surface is, you know, not horribly rough. It's not like this, where you don't have any sort of, you can't have any reflection because it's too, you can't have any reflection that perfectly matches the angle of the incoming light because it's too rough. We have something that's a little bit smoother. And so this surface is moderately rough, and we still have the flashlight we still have a flashlight shining light down here. But because the surface is rough, the normals are not facing, the surface is not facing directly up, so the normals are perpendicular to the surface. So we have this surface here, the normal is probably facing this way, and some of the light is actually hitting that surface right here, so the light is hitting this area, being reflected, and this is probably it needs to be reflected at an equal angle, so it needs to be somewhere over here, and then the surface normal would be about here for this little surface here, and then the surface here is pretty is kind of facing directly straight up, so then normal for this surface is here. And we have another surface over here, and the normal is down here. Our normal is always going to be the angle between the reflected direction for a given surface and the incoming light direction. But this object is made up of multiple surfaces, not just one smooth surface. So instead of having a tight cone of reflected outgoing light, we actually have a scattered cone of reflected light. So the cone is kind of wider, sort of this large. The light is really scattered compared to a specular reflection on a perfectly smooth surface where the outgoing light cone is the exact same size as the incoming light cone. So this time what we'll see for a model like this would be something that looks a little, first it's going to not be as bright, because the intensity is going to be, if we're talking about a physically based specular reflection model, the light that is going to exit, the intensity of light that's hitting the model has to be the same amount of intensity and energy has to exit the model, unless some was transmitted through the surface. But in this case there's not, so this same amount of energy here has to be the same amount of energy leaving. And so in this case the cones are the same size, so the intensity is the same size, so the incoming light is as intense as the outgoing light. But in this situation the cone is larger, so since we have the amount of light being spread out over a larger surface, it also has to be less intense, so it doesn't look quite as bright. But inside this cone of light that's being reflected, there should be kind of the center area should be a little bit more intense, because even though I drew all these rays kind of going in opposite directions, the rightmost boundary of light is over here, the leftmost boundary of light is over there, so that means the majority of light is probably in between, the exiting light is probably in between these two sides. So what we will see is a little bit of an area of a little bit higher intensity here. So this is a smooth surface, perfectly smooth surface, and this is a surface that's a little bit rougher. This is how lighting would work in real life. When we do lighting in a gaming engine, we have to take diffuse lighting into account. And diffuse lighting basically is the same thing, except for we don't really have a cone of reflected light. What happens is we have a light source that's like a flashlight, not a laser. It needs to be a wide enough light source, and we end up with the light supposedly is able to hit all areas, all parts of the surface, but still some of that light sort of decreases. We don't get as much light hitting all the way back here, and so this area looks a little bit darker, and that's what creates sort of the diffuse lighting model. But I'm betting you can probably tell that there's no real, that you're probably able to tell that you could take a diffuse lighting model and just, if the surface was getting more and more smooth, the cone would get smaller and smaller. So there isn't really a difference between the diffuse lighting model and the specular lighting model in real life. But inside the game, you have to have a diffuse model that you put down first before putting a specular model on top, because the way these models work inside the engine is that if you didn't have the diffuse lighting model down first, you would get an image that kind of looks like this, even for a rougher surface. And a reason for that is because in this situation we're still assuming that this is lit. This back here is lit, and it would be in real life. Because as I said before, there's no difference between diffuse lighting and specular lighting in real life, but inside of an engine it is, because the engine will look at your specular model and only take and will only basically look at this area. Okay, that was supposed to be. It will only model this area and ignore everything else, making it